In this module, we're going to have a relatively brief lecture so that you can take advantage of a number of different internet sources, but we're going to be looking at global climate change. We're going to start with your textbook's case history, which looked at potential consequences of global warming. There was a 300-year period from about 1000 to 1300 of the Common Era where Earth was considerably warmer than normal, and that's known as the medieval warming period. That was abruptly followed by the Little Ice Age, which I'll abbreviate LIE, which lasted from about mid-1400 of the Common Era to 1700 of the Common Era. And during this time, there was significantly cooler temperatures, and it made life difficult for people in Southeast Asia and Western Europe. The collapse of the Ankaran civilization in Southeast Asia is thought to be due in part to the onset of the Little Ice Age. If we look to Western Europe, we see crop failures during the Little Ice Age, and the population was devastated by the Black Plague near the start of the Little Ice Age. Going further into this case history, history tells us of the famous Viking explorer Eric the Red, whose voyage near the end of the 10th century was associated with a period of a relatively warm climate in the medieval warming period. Associated with that type of exploration was the Vikings' colonization of Iceland, Greenland, and parts of Northern America. And it was possible for colonies to thrive in Greenland and northern parts of North America during that time because of the warmer temperatures in the medieval warming period. The sea temperature, ocean temperatures, were approximately 4 degrees C warmer than they are now. The Little Ice Age started in the early 14th century, creating treacherous sea conditions, famine, and the spread of the Black Plague. Climate change is believed to have caused the abandonment of the Viking settlements in North America and Greenland. If we look at the fundamental data that speaks to us about climate change, we see that Earth's temperature has been gradually rising over the last 150 years or so. There hasn't been a steady rise. We see very cyclic changes. And we also see that there have been events such as volcanic eruptions that cause a general cooling process for a few years before the gradual temperature change resumes. This leads us to need to discuss the greenhouse effect. In the greenhouse effect, we recognize that the temperature on Earth is determined by 3 fundamental factors: the amount of sunlight that's received into the Earth, the amount of solar energy that's reflected and absorbed, and the amount of heat that's retained by the atmosphere. On Earth, we find that the Earth's surface is absorbing the shorter wavelength solar radiation that's incoming, and then it's radiating back longer wavelength infrared radiation. And now let's look at the absorption and reflection of both those streams, the incoming and the outgoing energy. If we look at the solar radiation incoming stream, we find that approximately 30% is reflected back into space by the outer atmosphere. About 25% is absorbed in the atmosphere, and about 45% of the incoming solar radiation is actually absorbed by Earth's surface. If we look at the outgoing infrared radiation, about 70% actually is transmitted through the atmosphere back into space, but about 30% is returned to Earth as heat that's reabsorbed by the Earth as a result of greenhouse gases. There are several atmospheric gases, water vapor, and several other gases, including carbon dioxide, methane, nitrous oxides, and CFCs, that work at trapping more heat and warming up the lower atmosphere. And it's similar to the effect of a greenhouse. The greenhouse, which uses a glass roof or glass ceiling to allow solar radiation in, but to trap heat inside the greenhouse, keeping it warmer. The collection of gases, including water vapor and the others listed above, function as effective greenhouse, keeping more and more energy trapped at Earth's surface. The concentration of greenhouse gases has been increasing in recent decades due to human activities, and we'll call those anthropogenic gases. When we look at or attempt to study past climate change, we can look at our actual instrumentation records of temperature since about 1860. Today, we have about 7,000 stations around the world which provide us an array of temperatures so that we can balance out annual cycles and variations across the globe to look at an average change in temperature across the Earth. We can also extend our knowledge of temperature variations back beyond when we actually were measuring temperatures using books and newspapers and journal articles and personal journals when people were recording what the weather patterns were in the period that extends beyond 1860, earlier than 1860. But books and journals only go so far in helping us understand the temperature of Earth in the past, and we need to create a paleoproxy record. This data refers to data that is not strictly climatic, but it can be a collection of correlated to the climate, such as the temperature of the land of the sea during times in the past, and we can gather information from ice cores, where we look at trapped bubbles, where we look at tree rings, seeing which years had adequate water and conditions to promote growth in the trees, and which years had only very small rings due to cooler temperatures, for example. We could have look at recorded pollens in sediments. We can look at coral growth. We can use carbon-14 data to try and get an understanding of exactly the years that particular tree rings or trapped air bubbles dated from. We can then look at carbon dioxide in the air bubbles and methane in trapped air bubbles to try and recognize that we can actually see those trapped air bubbles provide us a time capsule in understanding what the atmosphere must have been like at the time that those air bubbles were formed. This allows us to look at temperature variations that go back beyond when we actually had thermometers out there measuring temperature. Again, by using such things as tree rings that could be used from adobe villages in southwestern United States, providing information about which years had abundant growth and higher temperatures and which years had less growth in the trees and therefore associated with cooler climates or droughts. We can also use glacial ice bubbles or to go back several hundred years, and this provides us with an understanding of what our understanding of carbon dioxide measurements were during that period. We can actually extend this back to the last 2,000 years or so to recognize that carbon dioxide and other greenhouse gases have been rapidly increasing in the last 100 years or so. We can compare this abrupt change in the last 100 years to records of atmospheric carbon dioxide that go back thousands of years and see that there are variations that go back, or if we look over this period of time, that there are significant variations in carbon dioxide. But the carbon dioxide that we see in the increase in carbon dioxide that we see in recent years is unprecedented. You should also be aware that while carbon dioxide has been higher in the past and lower in the past than it is now, there's also been associated massive changes in Earth's climate during those cycles that we may not want to try and have to live through or ask future generations to live through. We can look at the change in temperature at the Earth over the last 1,000 years or so, and we see evidence of what we discussed earlier, the warmer medieval warm period and the cooler Little Ice Age from Earth's past. But when we compare that to the gradual trend that shows an increase in temperature over the last 100 years or so, we are first probably struck by, in this data, by how jumpy it is, how you can have very cool years immediately followed by very warm years, or very warm years, which are followed by years that are the next year can be suddenly much cooler. So to get rid of this jumpiness, we need to take a running average over a few years, and that leads to this trend. And this is probably the one where the actually spotting the gradual increase in Earth's temperature over the last 100 years is most evident. You can't really say that there was much fluctuation going on in Earth's temperature from about 1860 to about 1910. But if you look at the average change on Earth's surface since about 1910, we see a very gradual climb. It hasn't been true every year, and there's been decades where the climb has not continued, but over the last 100 years, we certainly have had a substantial increase in Earth's temperature. There are a number of different processes that help contribute to the gradual increase in temperatures that we're seeing on Earth's surface. The first that we'll consider is solar forcing. We can look at the historic record of the past 1,000 years and see that there's significant variability in solar energy, the actual amount of energy that's being released by the sun. The medieval warm period from around 1000 to 1300 AD is thought to correspond to a time of increased solar radiation, whereas the Little Ice Age, which it began in about the 14th century, it corresponds to a period of minimal solar activity. So this onset of the cooler period is a time when the sun was actually releasing less energy. The relative variation in the amount of energy being released by the sun, transmitted to the Earth, is very slight. It's only about 0.25%, but even that much variation has considerable impact on our atmospheric conditions. The next factor is volcanic activity, which we'll call volcanic forcing. So volcanic eruptions can release vast amounts of aerosol particles into the air. These are usually in the upper atmosphere, but they can linger for years, maybe a decade for some of the largest eruptions on Earth's surface. Aerosols function in reducing the solar radiation that's coming into the Earth's surface. Episodes of volcanic eruptions are thought to have contributed to the cooling during the Little Ice Age, or during portions of the Little Ice Age. So the volcanic forcing actually works to cool Earth's atmosphere in general by reducing the amount of solar radiation that reaches Earth's surface. Next, we'll consider anthropogenic forcing. Natural variability fails to explain the warming in Earth's temperatures that we see at the end of the 20th century. We can use mathematical modeling on anthropogenic forcing to recognize that a temperature increase of about 2 degrees C is typically associated with the doubling of the carbon dioxide in the atmosphere. We can expect significant global warming as a result of human activities as a result. Air pollution will cause a reduction in the incoming solar energy by about 10%, which will offset by up to 50% the expected warming that will come from the increase in the amount of carbon dioxide in the atmosphere. So pollution is actually helpful in that sense because pollutants help reduce the amount of solar radiation reaching the Earth, but the effect of the carbon dioxide trapping more of the energy that was being released from the Earth back into the atmosphere is stronger. You can look more into the negative forcing from aerosols and other pollutants using figure 1820. One of the indicators that we often point to look at evidence of global warming is the retreating sea ice and retreating glaciers. If we look from the period from about 1853 and look at the sea ice and its more extensive coverage of the North Pole at that time, and compare it to the sea ice in 2005 and the extensive retreat by September 2007, we see that we have a massive reduction in the amount of sea ice near the North Pole. Those are the pieces of evidence of climate change, and some of the web references in this module will help you identify more of these. But now we'll turn our attention to some of the potential effects of climate change. We can expect that a doubling in greenhouse gases then to cause about a 15 degree to 4.5 degrees C increase in average global temperature. We see a significant rise in sea level and melting of glacial ice due to the increase in temperature. The number of retreating glaciers on land is accelerating in many parts of the world. We can see significant effects on global climate patterns with increased drought, with more violent storms, with warmer weather, with cooler weather in other areas, and some areas get drier, some areas get wetter, some areas get much hotter, and some areas actually get cooler, but the overall trend is a warmer climate across the globe. So with the trends in global warming, we also see changes in the climate pattern. Global warming leads to significant variations or changes in the amount of rainfall and soil moisture that's present on Earth's surfaces, and so we can expect more droughts and more floods. We'll also have variations or significant changes to agricultural activities, altering of the crop growth cycle. And the world's food supplies are greatly are affected strongly by climatic factors, and such factors as desertification, where a drying up extended droughts can lead to an area being no longer useful for agriculture. There may be some areas where agricultural productivity increases, but the overall trend will be a reduction in agricultural productivity on Earth's surface. Global warming affects the frequency, intensity, and distributions of natural hazards such as hurricanes and other storms. And we've experienced some of those storms, such as Hurricane Sandy in the east coast of the United States. associated with the global warming, we can expect rises in mean sea level. Unestimated 40 to 200 centimeters increase or rise in the mean sea level is expected over the next century. Associated with this, we can see increased coastal erosion, retreat of the coastline up to 260 feet in open beaches caused by stronger wave action alone. And the stronger wave action is often attributed not just to the rise in sea level, but also to the more violent storms that can be expected in a warmer global climate. We then experience a landward shift in existing estuaries, and this can affect an area such as New Orleans, and which is already believed to have experienced a more intense Hurricane Katrina as a result of some of the wetlands lost off coastal Louisiana. This rise in sea level can have a disastrous impact on existing developments along coastal zones. This biosphere is the area where global warming may have its greatest impact, or the impact that we most care about. It's going to be causing a number of changes in the biosphere affecting both people and the overall ecosystem. There's going to be a risk of increased extinction to many species due to land use changes and habitat shifting. This is going to lead to a spread of infections and other diseases due to the migration of organisms that are associated with the habitat shifts. We'll have both land and oceanic components affecting plants, polar bears on land, bleaching of coral reef at sea, and the impact of future generations of humans. Please take advantage of the many internet sources that I point you toward this week. There's assignment 1 in this module, and you'll also see a quiz that as we have in all our modules, there's a quiz in this module as well as assignment 1.